All right, today we're going to be learning some about magnetism, and we're going to make little electric motors. So first, basic things about magnets. Here in front of me, I have a compass. So assuming I choose the Google Calendar or camera because it won't time out on me. Just once. So I take a video of this here, and we have compass. I spin it, and when it stops, okay, let's slow it down some. Okay, so when it stops with one side pointing north. So people noticed that a long time ago, and they said, well, let's call that a north-seeking pole. So it has two poles, a north and a south. Now we have learned previously that charges come in two types. And what do we call those two types? Positive and negative. Here, magnetic charges come in two types. And they call one north because it's north-seeking. And one south because it's south-seeking. Dismiss that error. Let's see what happens. Okay, it won't save the picture. That's a disappointment. Well, let's get rid of it. Maybe. Okay, it won't save the picture. I was trying to. Did you not see? You didn't see any of that, did you? My bad. User error. You should have said, not working. Demo would be better if we saw it on the screen. Okay, so we have this. And I can make it go around in a circle, but when it stops, it's always going to stop, so one side is pointing north. And that's the thing that people notice, and that's why they call that side north-seeking and the other side south-seeking. Just for grins, I'm going to see what happens if I try to take a picture here. See if it fails again or if it was because I had it in the wrong mode. Yep, nope. Dismiss, get rid of it. Okay, so still can't take a picture, but hey. So we have the two poles, the north-seeking and the south-seeking. Now, before I go further, here's another magnet. And I haven't checked to make sure that this one's okay. If I take this magnet, it has a north side and a south side. So north-seeking, what does north-seeking mean? Here, hold this one. What does north-seeking mean? Seeks the North Pole. So now we're going to take another magnet that has the side, no, I'm just pointing to it, that has the side that will seek the North Pole marked on it as N for north. And we will have my assistant here bring the N side up close to the magnet. So go ahead and bring her up a little closer so they can see. There they can see. Which side is seeking the north magnetic pole? Whoops. Whoops, that's not. Whoops might describe what I do as well. It turns out that because the north-seeking seeks the south side magnetic pole, that the north-seeking pole, which is seeking the North Pole, is seeking a south magnetic pole. So what does that tell you about the Earth's North Pole? It's the south magnetic pole, because of the way they defined the North Pole of a magnet. I find that rather humorous. Now, the magnet itself has the two poles, north and south. What happens if I break the magnet into two pieces? Then what do I have? Two magnets. What kind of pole am I going to have here? That is correct. Whoops. Now let's get back to the pin. This will be a south. What about the other side here? Yep, that's going to be a north. Magnets always come in magnetic dipoles. That means it always comes with both of the two types, the north and south. The reason for this, it goes down to a lot of things, but basically what makes a material magnetic is you have magnetic molecules, atoms, inside of it. And in something like iron, you have something that is pretty strong magnetically. But normally, iron is not magnetic. That is, I can't take one of these paper clips and pick up another paper clip with them. Right? It's not magnetic. This will stick to a magnet. I can bring it over here, and it sticks to that just fine. And if I put it on here so it's sticking to that, and then I come back over and try to pick up a magnet, well, I didn't do it long enough, but you can make it so it's temporarily magnetized. Anybody have experience with that? Well, here's what's going on inside of the magnet. The magnets have these little regions that we call domains. So you might have little regions broken up like, And each one of those behaves like a magnet of its own. And in a random material, those are oriented in random directions. So if they're oriented in random directions, when you add them all up, they just add up to 0. That is, you have each little piece is a little magnet, but the magnets are all just clumped together randomly so that if you add them all together, you have an average magnetism of 0. So it's not magnetic. If you want to make a permanent magnet, what you need to do is to get all those little domains lined up so that they're all pointing the same direction. Then if they're all pointing the same direction, you have a magnet. So to make a permanent magnet, to make this work, you know what I did? I took it up here, and I have a device that makes a strong magnetic field. And I put the side that said N into the side where I wrote, put north here. I'm going to do it reversed. I'm going to put the south side, the side that says S, into the side that says put north here. And then connect it. I press my little button, and what it did is it made a very strong magnetic field. And that very strong magnetic field aligned these things. But I put it in backwards, so now what's it going to do? It should go the wrong direction. So we put this back on here, just to balance it. And sure enough, it's now pointing that north is that direction instead of that direction. So I reversed the magnetic field of that. Now, of course, it doesn't hurt it, but in case I want to use this like for class next year, let me put it back to right. Just putting that strong magnetic field to make them align. And now it comes around and it will align the correct direction. So magnetism, the Earth must have a magnetic field with its north magnetic pole to south pole, its south magnetic pole to north pole, for it to behave, for compasses to behave like they do. Basic rules of magnets. Opposite poles attract. Does that sound familiar or odd? It's the same as with electric charge, right? Opposites attracted, and just like with electric charge, like poles repel. So you can play with magnets. I can take this magnet and this magnet, and if I put the north to south, they attract and I could pick it up. Put the south to south, no such thing, right? Because it's actually pushing apart. Now with strong magnets, it's much more fun. Where's the strong ones? Here they are. These are little rare earth magnets. They're very strong. take them apart for me. It is possible, but it's really difficult. You have to think about it. You can't pull it straight apart. You never get that. You have to slide it.
Oh my word, even sliding.
Yeah, even sliding it's really tough. You're halfway there. Oh, no. Okay, so sure. Everybody can try. It's physics. We're playing. We're having fun. There we go. Now, don't bring them together. Now that we have them separated, what do we do with this? Magic! I don't know if you guys like watching magic shows, but they like have these little street magic shows where somebody shows these little magic tricks. And they try to be really sly. And they have something like a little fly on the table. And they're sitting here all crumped up on the table, and the fly moves. Right? How do they do that? How do you think they do it? Yeah. Cool things you can do. Okay. It's tough. They came back together. But you can put like one on one side of my finger, one on the other side of my finger, you know. They stay there, right? Kind of cool. Okay, so now I'm being careful. I have these so it's attractive. You saw it pick it up when I got close. Now I'm going to flip this one over so it's repulsive. What do you think will happen when I get close? Almost right. Okay, you gotta watch carefully. Oh, it actually didn't do because it ran off the table. What it does is it will flip it over and then pull it up. But because there you saw it flip it over, pull it up. Because it's very strong forces. So of course you play with these all you want during lab, because learning about how magnets work, that's part of physics. Now what we're actually going to be doing for lab is making electric motors. So how does an electric motor work? We have a homemade model you're going to make as well as a pre-made model. And I want to look first at the homemade model. So your homemade model is going to be like this. Instead of rubber bands, we're just using black tape wherever it went, electrical tape, yeah, up there, to tape our little, don't break them, paper clips to hold onto the positive side and the negative side of your D cell. So everyone's going to have a D cell. Well, everyone, you'll work in groups of two. Each group of two will have a D cell. You're going to have to take about a meter of wire from this. So just unroll a meter, cut it off, and then wrap to make a coil like that. I just put 2 fingers in there and wrap it around my 2 fingers. Then you loop it a few times here and come off. Just come off with one piece. Loop a few times here and come off. What happens with that coil is interesting. It takes a lot of work to get there with physics, but it turns out that if you have current, we all know what current is now, if we have current that goes in a loop, that current is going to create an electric field, or not electric field, a magnetic field. Magnetic fields are the things that the magnets are interacting with, and so this will behave like you have a bar magnet. So here I have my little loop I made, and when I put current through it, it'll behave like I have a bar magnet with north pointing the way my finger is. Or if I reverse the direction of the current, it would be pointing the opposite direction. So depending on the direction of the current, north points the opposite direction. So this is going to behave like a magnet when you connect it to the electricity from your battery. And so if you have this, you have it on top of your battery, where yeah. Grab me one, man. Help me out. Thank you. So we're going to have our battery here, put a little magnet on it. You've got your little risers that is going to hold this. And like this, we might have north pointing down from this coil and north pointing up from the magnet below. If it's north north to north, what's it going to do? Repel. So it's going to try to push it away. So it's going to rotate it away. And of course, it'll rotate it away until we get so it's north to south, it's attracting. So we can make it rotate half a rotation. But there we have a problem. Because after half a rotation, it's going to try to keep on going. And then it'll be stopped because it wants to keep the north to south. So we have to stop this from being a magnet for half of a rotation. We only want it to be a magnet for half a rotation, then not a magnet for the other half. How we do that is after you finish making your coil like this, put it on something flat. I did it on the table, and that's bad because then I scratched the table. But you put it on something flat like Colby's lab book. And then you scrape, this is emery paper, we'll get some more. You scrape off the enamel coating. This wire has enamel coating so that it doesn't conduct to things that touch it. And so you just put it down and scrape off the enamel coating on both sides of your coil. Both sides here, but now you can see the black side insulated. The pink or the brassy side, the shiny side, that one's conducting. And so now for half of a rotation, it'll be conducting. For half a rotation, it'll be not conducting. So then it's turning on half a cycle, turning off half a cycle, so you can skip the repelling cycle. So then you're going to make your motor work. You have to make your motor, now you have to give it a little flick probably to start it, but it needs to keep running. Not just give a flick and it stops because, well, things do go for a while because of momentum until they stop, but actually keep running. You have to have Toussaint sign off, yes, I saw yours running. And after you have that, then all you have left to do is to take one of these. I see where all my stuff went. And you need to make this operate. Now, this is a little different than what we saw. What's the first thing you notice that's different than my homemade motor? Okay, well, it's already all connected. Yes, that is true. So, something more? Does it have a coil like mine had? Yes. It has 3 of them. It has 3 coils. And if you look here, it has connectors coming up, and it has 3 different connectors. As it rotates around, your connection is going to change from one set to another. So you turn on this coil for 1/3, this coil for 1/3, and this coil for 1/3. So you're getting maximum torque all the time. But only one coil is working at a time. This here contains the magnets. This one is missing one. Still got 3 out of 4 magnets. So you have the magnets just like before. You have that coil. Ideally, it would just go like this. But the problem is these brushes don't quite make contact. So you have to sit here with your fingers and lightly make contact and get this thing to rotate and get to, oh, I was so close there. I had it starting, but you have to get it to rotate on its own again, and it'll be pretty clear when it's on its own. There we go. And then have the TA sign off. I saw that you had that rotating on its own. Then you have some questions to answer about the motors, and you're done. Questions? All right. Have fun.
Speaking, not a thing.
Words. What?